Very simply, optimization is the best way to perform a specific task. In economics and the social sciences and business, there are many examples. We can think of a manager trying to maximize profits. And how are they going to maximize profits? Well, they're going to maximize profits thinking about labor as an input. So how much labor should they hire in order to maximize profits? You can look at a doctor who might want to know, well, what's the best time of day to inject a drug to avoid complications? We'll look at an example. Farmer might be trying to choose how much fertilizer to use to maximize profits. And we might look at an oil company which is extracting oil per minute, coming out of the ground, and they might be interested in at what rate they should extract oil in order to get the most revenue from it. Now, how can we use calculus to answer these interesting questions? Well, we're using univariate calculus, so we have to keep things relatively simple. But number one, in general, you would want to model the problem. So write down a mathematical objective function. And since we're using univariate calculus, we would just have one independent variable, x. How is x going to affect the thing that we want? Once we've written down a model that can be quantified, we're going to try and solve for the variable of interest. So we're using univariate calculus right now, and so we're just going to have one variable of interest. The last step might be calculating f of x, if that's required. For example, we might want to solve for profit. So we found the x that maximizes profit. We'll know the value of x. Maybe x is equal to 16. Well, if x is equal to 16, how much profit are we going to earn? And generally speaking, the solution to all of these problems that we discussed is going to occur at something called an extreme point. Now, what is an extreme point? Well, very simply, an extreme point is either a maximum or minimum value of f of x. Let's start with an example. So here we have a model. So we've modeled the problem, and f of x is going to be equal to this thing right here. Now, maybe we want to try and find if it has any extreme points. Right? The question says, does it have a maximum? Does it have a minimum? The max and the min would be extrema. They would be extreme points. Well, a very simple and straightforward way to solve, or I should say to answer this question right here, does it have a maximum, does it have a minimum, is to graph the function. And if we graph the function, we can see it's this nice quadratic line. Goes like that. And does it have a maximum? So we're looking at, we can kind of imagine that there's an unlimited domain. Let's just say that the domain here is, x has to be less than infinity and more than negative infinity. And so it's going to go off. We know, looking at this, that the maximum occurs when x is equal to 2. And when x is equal to 2, f of x is equal to 3. And we can see that. We know if we were going to do this a little more formally, with x minus 2 squared is always positive. And if we have negative x minus 2 squared, that's always going to be negative. And so the only way to get f of x very large is to let x be equal to 2. So when x is equal to 2, f of x is a maxima. And we have f2 is equal to 3. So it can't be any larger than 3. So we have one extreme point, and it's a maxima, or maximum. Is there a minimum? Well, the answer is no, because if x was equal to infinity, or x was equal to negative infinity, then f of infinity is going to be equal to infinity. This expression goes off to negative infinity, and I should have a negative there, negative infinity. And so we can write f of x has no minimum. If you add in a very large positive number, or a very small number, a very large negative number, then f of x has no minimum. It just keeps getting smaller and smaller and smaller. So f of x has one extreme point. Now, very formally, we could write, let C be in the domain D. So this is the domain. And this whole thing is a maximum point for f, the function f. This is our function f. If f of x is less than or equal to f of c for all other x that are in the domain D. And so if we look at the graph, we have a graphical expression, illustration of this very formal point above. And so if C is a max, if it's a maximum, which it is on this diagram, then if we pick some x over here, I'll call it x1, or if I pick x2 over here, call that f of x2, then our formal definition of a maximum has been satisfied. So this thing up here, definition for C to be a maximum value for f. Now let's look at this g of x function. We can see that we have, it's essentially g of x is equal to negative f of x. And so g of x is equal to negative 3 plus x minus 2 squared. And we can see if we want to find, in this case, we're looking for a minimum. If we're looking for a minimum, then when x is equal to 2, g of 2 is equal to negative 3. And this is a minimum. How do we know it's a minimum? Well, we've got we're adding x minus 2 squared, and so this thing is always positive. So the lowest value for g of x is the function g when x is equal to 2. And that occurs right here on the diagram. You can see that if I draw a little dotted line over, we end up with exactly what I described in words in mathematics previously. Now, is there a max? Is there a maximum? Similar to the previous one, no. There is no maximum. As x approaches infinity or x approaches negative infinity, g of x becomes larger and larger. So it doesn't approach to a single value, a number, a real number. It just keeps getting bigger and bigger and bigger. And so we say there is no maximum. It just keeps growing indefinitely. Now, to define a minimum, we can write that, suppose we have the value d, and that d is in the domain. This whole thing here is or the point D specifically is a minimum for G if G of x is larger than or equal to G of D for all other x in the domain D. So if we look at the diagram and we look at x is equal to D, you can see that the lowest value for G of x is when x is equal to D, right here. And if I pick x1 randomly, I'm going to end up with a larger value, y-axis value. Similarly, if I pick an x2 value over here, or maybe it doesn't matter as long as it's not at point D, so I could pick one right here, you can see that G of x2 is going to be larger than G of D, and this definition above is satisfied.